Hello everyone. Today we are going to discuss modulus of complex sine and cosine functions. To find a formula for the modulus of complex sine and cosine functions in terms of x and y, we first express these functions in terms of their real and imaginary parts. We know that y is any real number, then sin hy can be written as e raised to y minus e raised to minus y divided by 2 and cos hy equal to e raised to y plus e raised to minus y divided by 2. So sin iy equal to e raised to iiy minus e raised to minus iiy divided by 2i, which is equal to e raised to minus I minus e raised to I divided by 2i, which is equal to I into e raised to I minus e raised to minus I divided by 2 equal to I sin hy. We know that 1 by I equal to minus I, and cos iy equal to e raised to iiy plus e raised to minus iiy by 2, that is equal to I square equal to minus 1. So e raised to minus y plus e raised to y divided by 2, that is equal to e raised to y plus e raised to minus y divided by 2 equal to cos hy. So cos z equal to cos x plus iy equal to here z equal to x plus iy. So cos z equal to cos x plus iy, that is equal to, we can know the expansion of cos a plus b. So likewise cos x plus iy equal to cos x cos iy minus sin x sin iy, which can be written as cos x cos hy minus I sin x sin y. And sin z equal to sin x plus iy, that's equal to sin x cos iy plus cos x sin iy, which is equal to sin x cos y cos hy plus I cos x sin hy. Now we are going to find the value of mod sin z square, which is equal to sin s cos hy whole square plus cos x sin hy whole square, that is equal to sin square x cos h square y plus cos square x sin h square, which is equal to, we can take sin square x out, then sin square x into 1 plus sin h square y plus 1 minus sin square x sin h square y. We know that cos square x equal to 1 minus sin square x and cos h square y equal to 1 plus sin h square y. So that is equal to sin square x plus sin square x sin h square y plus sin h square y minus sin square x sin h square y, which is equal to sin square x plus sin h square y. Now we can find the value of modulus of cos z square, which is equal to cos x cos hy whole square plus minus sin x sin hy whole square, which is equal to cos square x cos h square y plus sin square x sin h square y, which is equal to cos square x into 1 plus sin h square y plus 1 minus cos square x sin h square y. We know that sin square x equal to 1 minus cos square x, and then cos h square y equal to 1 plus sin h square y, which is equal to cos square x plus cos square x sin h square y plus sin h square y minus cos square x sin h square y, which is equal to cos square x plus sin h square y. We know that hyperbolic functions sin hx is unbounded on the real line. As a result of this fact, the expression for modulus of sin z square and cos z square can be made arbitrarily large by choosing y to be arbitrarily large. Thus, the complex sine and cosine functions are unbounded on the complex plane. That is, there does not exist a real constant capital M, so that neither sin z modulus of sin z less than M nor modulus of cos z less than M for all z in C. Next, we are going to discuss analyticity of complex trigonometric functions. We know that e raised to z is entire function, that is, it is analytic for all z. So, cos z and sin z being linear combinations of analytic functions e raised to iz and e raised to minus iz are analytic for all values of z. Then the derivative of complex sine and cosine functions can be found using the chain rule of differentiation. So d by dz of sine z equal to, we know that sine z equal to e raised to iz minus e raised to minus iz divided by 2i. So d by dz of sine z equal to d by dz of e raised to iz minus e raised to minus iz divided by 2i. 1 by 2i take outside, so 1 that is equal to 1 by 2i into d by dz of e raised to iz minus, that is equal to 1 by 2i into I into e raised to iz plus I e raised to minus iz. So that is equal to e raised to iz plus e raised to minus iz divided by 2, which is equal to cos z. So we prove that d by dz of sin z equal to cos z. So next we are going to find the derivative of cos z. So d by dz of cos z equal to d by dz of cos z we can written as e raised to iz plus e raised to minus iz divided by 2, which is equal to 1 by 2 into d by dz of e raised to iz plus d by dz of e raised to minus iz, which is equal to 1 by 2 into I e raised to iz minus I e raised to minus iz, which is equal to I by 2 into e raised to iz minus e raised to minus iz, which is equal to 1 by 2i, sorry, minus 1 by 2i, because 1 by I equal to minus I. So I by 2 equal to minus 1 by 2i into e raised to iz minus e raised to minus iz, which is equal to e raised to minus of e raised to iz minus e raised to minus iz divided by 2i, which is equal to minus sin z. So d by dz of cos z equal to minus sin z and d by dz of sin z equal to cos z. Like this, tan z and sec z are analytic at everywhere except at the points where cos z, that is denominator of tan, equal to 0, cos z equal to 0 when z equal to pi by 2 plus n pi, where n equal to 0 plus or minus 1 plus or minus 2, etc. Similarly, cot z and cosec z are analytic at every point, at everywhere except at the points where sin z equal to 0, that is z equal to n pi, which is equal to n equal to 0 plus or minus 1 plus or minus 2, etc. So d by dz of tan z equal to 6 square z, d by dz of cot z equal to minus cosec square z, and d by dz of sec z equal to sec z tan z, d by dz of cosec z equal to minus cosec z cot z. Thank you.